Hey everyone, welcome to CS358 final project presentation. My name is Renzo Liu. This presentation focuses on Python multi-thread parallel computation. So let's start today's presentation with parallel computation. The parallel computation is the simultaneously execution of multiple calculation or processes to solve a large problem faster. I bet everyone in CS358 knows this unless you do no homework and no exam. Just a joke. Basically, there are two ways for parallel computation. Multiprocessing and multi-threads. Multiprocessing uses distributed memory, which has strong isolation. Even one process crashes, others still works. This synchronization between processing is still by operating system. Multi-threads uses shared memory, which is weak isolation and faces risk condition. The synchronization between threads is still by log and mutex. Why Python is special for parallel computation? Because of Python Global Interpreter Lock. It is a mutex that protects access to Python objects, preventing multi-threads from executing Python bytecode at once. The GIL prevents risk condition and ensures thread safety. In short, this mutex is necessary mainly because Python's memory management is not thread safe. This definition comes from Python Wiki. Okay, now let's see Python's history on parallel computation. Python's support for parallel computation has evolved significantly over 3 decades. From 1994 to 1996, Python 1x introduced its first parallelism mechanism through low-level thread module, later expanded into high-level threading interface. Later, around 2001, the GIL became a well-understood and central part of Python's execution model, enabling safe multi-threading but preventing true parallel execution of CPU-bound code within a single process in Python 2.1 to 2.2. In 2008, Python supports multiple processing module, which allow Python programs to finally achieve real multi-core parallelism by using independent processes instead of threads. 2023, Python 3.12 delivered the substantial improvements to the interpreter itself, reducing context switching cost and making it more efficient. This year, prototype GIL-free builds based on PEP 703 bring the possibility of true multi-threading parallel execution for CPU-bound workloads, potentially reshaping Python's entire concurrency landscape in Python 3.40. However, Python 3.40 does not support GIL-free in formal release version. Calling GIL-free is not supported. But we can use Python 3.14t for real GIL-free, where T means free thread build. You can install it with the link at the bottom. Changing multiprocessing to multi-threads is easy in Python. Here I use matrix multiply as an example. I think this is from our project 1 or lab 1. I can not remember very well. So in the code, instead of using executor from the process pool executor, multi-thread uses executor from thread pool executor. You can see the red line I mark here, and it is pretty simple to parallel compute in Python. Basically, Python does everything for you. In this experiment, I use a 1000 times 1000 times size matrix and 1 to 4 as number for the processing and the threads. Here's the result. we can see that multiprocessing takes about 72 seconds for one core, 39 seconds for two core, and 23 seconds for four core. And multi-threads takes 92 seconds for one, 44 seconds for two, and about 30 seconds for four. Multiprocessing is faster than multi-threads in each task, we can see, right? When worker number increase, the difference between them is getting smaller, and so that in test one, the difference is about 20 seconds, but in test two and test four, the difference is about 5 seconds. So it is obviously that multi-threads speed up when you use more threads, and it does better in speed up comparing to the multi-processing. The multi-thread speed up to 2.11 times in test 2 and 3.15 times in test 4, which is much better than uh, multi-processing in speed up, right? Like it has 1.86 times speed up in test 2 and 3 times speed up in test 4. So, but after all, the absolute speed of multi-threads is slower than multi-processing, and I think it is not something unimportant to ignore, like the example we talked in class between the Maple and the C's speed in parallel computation. So why? Why multi-thread slower than multi-processing? The first reason is very significant in this experiment. is a CPU-bound task. Of course, multiprocessing performs better than multi-threads. The second reason is that Python list is a non-continuous memory. Both multiprocessing and multi-threads are slowed down by it. And I think Python 3.14t is a beta version. I guess dispatch is now smart enough, and there are mandatory mutex while processing, which slow down the speed. And the last problem for Python 3.40t is that it doesn't support package like NumPy. In this case, it's hard to optimize it. Comparing to C, native Python is way too slow. Like in our result, C takes less than 1 second to finish, and the Python takes seconds or minutes to finish the task. So 100 times difference between them. In this small experience, C is much more powerful than Python. So I have to ask a question: why we still need Python to do parallel computation in this case? Well, there are many reasons. First of all, not everyone studies CS, ECE, and know how to program. My bio roommates always ask me questions in Python and R, which is kind of stupid in my eyes, but they don't really in programming like we do. And Python is a fancy, simple language comparing to C, C++, and Java. It is young, powerful, and reliable language compared to some old language like R, which language always crashed when I use it like 2 or 3 years ago, and I think it's not that powerful as Python does, right? I heard they finally make R robust this year, which is a really nice news for those bio or some big data science people. What's more, Python does involve in many big data fields such as machine learning, artificial intelligence, biostudy, economy analysis, and environment study. There are lots of packages like PyTorch, Pandas, NumPy, and SciPy, which make people's work much easier comparing to C. So in our class, a MapReduce framework called Hadoop is also introduced. Even though it is powerful, it is not very suitable for everyone. Some personal user may now have the accessibility to a cloud server, and other people may want to use more complex parallel computation, but not MapReduce in some situations. So therefore, Python has its own advantages in parallel computation. Easy to start, many packages support your work at a low cost. It is not that fast like C or C++, but it still gives people who knows nothing about programming a choice. I think these are the reason why Python keep updating its parallel computation with multi-threads beyond multiprocessing. It just gives people more choice for their uh, work. So this is all for my today's presentation. Thank you for listening, and here is some reference I find for Python 3.14t, which is a GIL free version. If you have interest in, you can take a look at to this to these links, and you can also find the C Python link in the previous slide. You can, if you want to try, you can download from it and ask like GPT how to download it if you really don't have any idea how to start with it. Okay, so thank you. Bye bye.